Good afternoon, folks. How's it going? This is Mike coming back at you with another video on Foundations of Math 2. In this video, we are going to do a little bit of a quick overview of some other types of functions that we have out there in the big world of mathematics. We're going to get into quadratic functions and then introduce the exponential function, and in our next video we will wrap it up with another different kind of function. But let's get right into quadratic functions. You may be wondering, what the heck is a quadratic function? A quadratic function is a function that is of the form ax squared plus bx plus c. Just as a bit of a review, you were introduced to the f of x notation perhaps from one of our previous videos. This just takes the place of y, so we could say y equals ax squared plus bx plus c, but now we don't write y, we just say f of x. In this thing right here, a, b, and c are all real numbers. A is not equal to 0. That's the one thing that we can't have being equal to 0. And if you look at the graph of a quadratic function, something of roughly this form, you get what's known as a parabola. Now here I have graphs of two separate parabolas here. As we can see, one opens downward and looks like a frown, and the other one opens upward and it looks like a smile. So the question is, in which case do we have which one? How do we know which one is which? Well, if a, which is that number in front of your x squared, if that number is negative, then your parabola is going to open downward. It's going to look something roughly like this. If your a value is positive, then your parabola is going to look something like what we have at the right here. It's going to open upwards. Now, on every parabola, we have two important features. First one is we have the turning point. There's always one turning point on a parabola, and that turning point is called the vertex. If that number in front of your x squared is negative, then your vertex is going to be the highest point on the graph of your function. If your a value is positive, then your vertex is going to be the lowest point on your graph. So a negative, vertex is your highest point. A positive, vertex is your lowest point. The other feature that every parabola has is this imaginary vertical line where if you take the left half of your parabola and you fold it over that dashed line, that it will land perfectly on top of the right half. What this vertical dashed line is called is the axis of symmetry. Draw the arrow to that vertical dashed line there. It's the axis of symmetry, that is. Now, we want to know what are the x and y coordinates of your vertex, and then what is the equation for this axis of symmetry. Well, the x coordinate of your vertex and then the axis of symmetry are both the same x value. That x coordinate can be found by doing the following calculation. Your axis of symmetry and the x coordinate of your vertex is given by minus b over 2a. Again, you're taking your b and your a values from here So that's what we are going to use there. The only thing we're missing is the y-coordinate of our vertex. Well, if you take this x value that you just found and you substitute it back into your quadratic function, then you can see what your y-coordinate is going to be. And then you have your vertex and your axis of symmetry. Now, with linear functions or linear equations, as we saw from one of our previous videos, those are fairly straightforward to solve for x. But these things are nastier. It's not as simple to solve a quadratic equation of any kind. So how can we find a value of x such that if I wanted to find when this thing is equal to 0, what x values would make that true? What x values would make this thing right here equal to 0? Well, luckily, we have a special formula that we can use to figure out when something like this would equal 0. It's perhaps a formula that you have heard of at some point in the past. Maybe for some of us, not so far back. Maybe for some of us, it's been a little while. But that formula is called the quadratic formula. And this is a surefire, concrete way to find all the solutions to the equation ax squared plus bx plus c is equal to 0. And your formula is right here. X is equal to minus b plus or minus the square root of b squared minus 4ac, and that's all over 2a. Now, this is sort of an ugly looking formula. It's not the prettiest looking thing in the world, but nonetheless it does help us get to the correct answer. It is something that we can use. Now, maybe this plus minus thing here, maybe that's looking a little odd to some of us. When we put plus minus here, what we're actually doing is we're actually coming up with two separate x values. One where we do minus b plus the square root of b squared minus 4ac all over 2a. That's one of my x values. And then my other x value is x equals minus b minus the square root of b squared minus 4ac all over 2a. So that plus minus there actually means two roots, use each one once. And we're going to see very shortly where do we use these quadratic functions in real life, and how can we use this formula here to help us find out some key pieces of information in those contexts. So like I just promised, where do we use these quadratic functions? The most common application that we use quadratics in is when we model projectile motion. Picture you have a cannonball inside of a cannon, and you set the cannon off, and the cannonball is flying through the air. Or pretend that you're launching a toy rocket, and the rocket has a horizontal component to how far it travels and a vertical component to how far it travels. These are two examples of things being in projectile motion. Well, we have a formula that we can use to model the vertical position of an object that is in projectile motion at any given time t. That formula is s of t equals minus 16t squared plus v naught times t plus s naught. V naught, what the heck is that thing? That is your initial velocity in feet per second. That is how fast is this thing traveling right when you fire it, or right when you throw it up into the air, or whatever. S naught is the starting height in feet. Your object could be starting at the ground, but it doesn't necessarily have to be. It could be starting, say, 20 feet up off of the ground. So that 20, that would be your S naught. And then S is the height of the object at any time t. And, of course, height is in feet. Now, just as a quick note, some of you may be wondering, wait a second, we have t's here instead of x's. I thought we use x's as the variables inside of these function things. Well, yes, it is common, or yes, it is true that for the most part we will use x as our variable. However, you don't necessarily have to always use x. T is in fact the second most common letter that we use to stand for the variable in a function. All right, so we're going to use this formula here to answer our following question, which does have several parts to it. So suppose a ball is thrown upward from a height of 20 feet with an initial velocity of 64 feet per second. Write the model that represents the vertical position of the ball at any time t. What is the maximum height the ball will reach? And at what time will the ball hit the ground? All right, so first part of this, we need to write the model that represents the vertical position of this ball at any time t. So we are going to use this thing right here, this s of t guy, but we need to label in some missing pieces of info. We need to make some substitutions here. We need to substitute in for the v naught and the s naught. Well, we're told the ball is thrown upward from a height of 20 feet. So this ball is starting 20 feet higher than the ground, so that's my S naught. That's my starting height. And we're told that it's thrown upward with an initial velocity of 64 feet per second. Oh, keywords, that 64, that's our V naught. So our model here that we want to use is minus 16t squared plus 64t plus 20. So there's part one. We have the model that represents the vertical position of this ball at any time t. Part two, what is the maximum height the ball will reach? If we think back to the beginning of this video, we said that if you have a parabola that opens downward, as we do on the left-hand side here, then the vertex is going to be the highest point on the graph of our function. If we look at our model, that number in front of my t squared term is negative. So we have a parabola that is indeed going to open downward. So to find the maximum height that the ball reaches, that's the same thing as finding the maximum point on the graph of this quadratic function. And the maximum point on the graph of this quadratic function is going to be at the vertex. We saw how we find where the vertex is happening at. We can at least find the x-coordinate by using this basic formula, minus b over 2a. So let's do minus b divided by 2a, and we'll calculate at what time our maximum height happens at, and then we'll take that time, we'll plug it back into S here, and we'll find out what that maximum height is. So the max height happens at t equals minus b divided by 2 times the minus 16. So I have minus 64 divided by minus 32, or a positive 2 seconds. So now to find that maximum height, I take this value of 2, I plug it in for t here in s. S of 2 equals minus 16 times 2 squared plus 64 times 2 plus 20. 2 squared is 4 times minus 16 is minus 64 plus 64 times 2, 128 plus 20. And when I add or subtract these numbers up, I get a positive 84. So this is the maximum height that this ball will reach. It's going to reach a max height of 84 feet. So that was part 2 of our question. Part 3, at what time will the ball hit the ground? This thing is the height at, or it gives us the height at any time t. We want to know at what time t will this height equal 0. So what I need to solve for is t in the following equation. Minus 16t squared plus 64t plus 20 is equal to 0. And to solve this, we are going to use that lovely little quadratic formula that we saw earlier on in this video. So our t value is going to equal minus b, minus 64, plus or minus the square root of b squared, 64 squared minus 4, times my a value of minus 16, times my c value of 20, all divided by 2a, or 2 times a minus 16. So now we have some ugly calculations here. Let's take care of what's inside of our square root first. We solve the minus 64 plus or minus. 64 squared is 4,096. Now note that we have a minus 4 times a minus 6, so that product is going to be positive, and 4 times 16 is 64, so this is plus 64 times 20, and that gives me 1,280, and that's all over 2 times negative 16, or negative 32. And add up the two numbers that are inside of the square root, we get 5,376. So this is where we're at right here, negative 64 plus or minus the square root of 5,376, all divided by negative 32. So we said, when we introduced the quadratic formula, we said that we're actually going to come up with 2 separate values. In this case, 2 separate t values. One for when we use the plus, another one for when we use the minus. So we're going to do these 2 separate calculations negative 64 plus the square root of 5,376 divided by minus 32, or negative 64 minus the square root of 5,376 divided by minus 32. So we are going to do these two calculations. We're going to plug these kind of ugly looking things into our calculator, and we're going to see what values we get. And I didn't specify within the question as to how many places you had to round to, but let's just say we're going to round to 1 decimal place. So I'll let you go into your calculators. If you do the square root of 5,376, you'll get some number. Subtract 64 from that, you'll get some new number. And now take that number and divide it by negative 32, and you find that t is equal to negative 0.3. Time here was in seconds, and we said round to 1 decimal place. To get the other one, take that square root of 5,376, multiply it by a negative 1. Then subtract 64 from that number. You'll get some new number, and then divide that number by negative 32, and you're going to get t is equal to approximately 4.3 seconds. Now, the question said, at what time does or will the ball hit the ground? There's only one t value. There's only one answer that we're going to have here. And why it's only one is really just sort of a matter of common sense. We can't really have a time value being negative. We can't have a t value being less than 0. It doesn't make sense. We can't go back in time and figure out when this thing would have hit the ground. So we have to sort of, for that reason, cut that guy out and say that the ball will hit the ground after 4.3 seconds. So there we go, guys. There's a very common real-life use of quadratic functions, specifically in modeling projectile motion and finding out basic yet important pieces of information, like when will the thing finally hit the ground after being launched up in the air, or when will this thing hit its maximum height, and what is that maximum height going to be. So this is just a little bit of an overview of quadratic functions here. Next up, I want to talk about a different kind of function, the exponential function. What the heck is an exponential function? An exponential function is a function that is of the form c times a raised to the power x. So unlike any of the other functions we had seen beforehand, x is not being raised to some power that's a number. It's not x raised to some number power a. Now it's some number a being raised to the power x. So c times a raised to the power x. A and c are non-zero real numbers, but also a has to be a positive number that is not equal to 1. It's very, very important that a is positive and not equal to 1. If a was equal to 1, then if we raised 1 to any power whatsoever, we would just get 1. And our graph would not look like what we're going to see very shortly. So this is the exponential function. This is the general form of it. Now, based on what your a value is, based on what the base is on that variable x there, that will sort of impact what the shape of our graph looks like. I have the graphs of two different types of exponential functions here. If a is greater than 1, then we're going to have the graph on the left. The function is going to increase or go up as we move to the right. And it's going to start to shoot up very, very fast. If A is between 0 and 1, then we're going to have our graph at the right here. This exponential function is going to start to come down very quickly, and then it is going to begin to flatten off or level off as we move farther and farther to the right. Now, I will say that no matter what your base is, every exponential function has the same point in common. They all have the point 0, 1 lying on their graph. So if you take 0 and plug it in for x and make that the power of some number, then you are going to get 1 out. And this is for things of the form a raised to the power x. We're not including that c value out front here. Both these graphs are for f of x equals a raised to the power x. There. And last thing that I want to mention in this video, you see how these exponential functions seem to be getting closer and closer to the x axis here. You may think that they're going to touch and they're actually going to cross through, but that's actually not quite the case. With this particular type of function, whether your a value is between 0 and 1 or if it's more than 1, doesn't matter. The function is going to get really, really, really close to this x-axis, but it's never going to actually hit it. And there's a name for a horizontal line that your function gets really, really close to, but never actually touches when we go far out. And it's called a horizontal asymptote. Horizontal asymptote. I'm not going to go into much detail as to how we find these things for other types of functions and what's the technical definition of them. That's for a future course, but I just wanted to introduce you to this particular property. So guys, that's it for this first video on this section of some newer kinds of functions. In the next video, we're going to talk about some real-life uses of the exponential function, and then another function that is related to it. So if you have any questions or comments, please be sure to reach out to me, guys. Send me emails, send me postcards, send me texts, flare signals, SOSs, whatever you have to do. Otherwise, until the next video, take it easy, guys.